Hello everyone, I've got a Key Stage 4 chemistry video here on the process of cracking. Now, on a previous video that I've done on fractional distillation, I spoke about how crude oil essentially comprises of these really long hydrocarbon chains, and what we essentially do is we get fractions from that, we break them down into smaller, more useful products. Now, these crude oil fractions can be further broken down into even smaller molecules, and that is what we mean by this. That is what cracking is. It's breaking down and splitting into smaller molecules these crude oil fractions into smaller, more useful products. Now, I said that these fractions are made of hydrocarbons, so let's just quickly remind ourselves of that. A hydrocarbon is something that purely has two things in it, one of them being carbon and the other quite obviously being hydrogen. But the one I've drawn here, CH4, methane, isn't a particularly long hydrocarbon. So what I'm going to use is another example, and this one that I'm going to use is C10H22. I'm not going to draw that out as a long molecule, actually drawing the molecule, because it takes up quite a bit of room. But what we've got there, C10H22, is a fraction that we can refer to as paraffin. Now, paraffin is a long chain hydrocarbon. That's what we're calling this. This is a long chain hydrocarbon. Now, whilst useful, we could get something more useful from that. Now, paraffin, it usually has about 10 carbon atoms in, but we have too much of this in crude oil already. So what we're going to do is we're going to break it down by a process of thermal decomposition. So we're going to break this down, and I'll just make a note there, that's by thermal decomposition. Now, I'm hoping you can guess that by thermal it means we're using heat. So we need a lot of heat to break these large molecules down. There are strong covalent bonds within this hydrocarbon chain. Covalent bonds form between atoms of non-metals and other non-metals, and as both carbon and hydrogen here are non-metals, and we've got these strong covalent bonds that we need to break. So in the process of thermal decomposition, what we're going to do is we're going to get from this paraffin, we're going to break it down, and we're going to get something perhaps like this. C8H18 and C2H4. Now, C10H22 paraffin is an alkane. That's an alkane molecule because there are no double bonds. What we've got here, CH818, if we follow the general rule for alkanes of CnH2n plus 2, the formula to work out how many hydrogens you have, what we've got here is something called octane. Now, octane contains 8 carbon atoms, and that is useful for petrol. But what we've also got is this C2H4, and that is called ethene. Now, ethene is an alkene. So we've got a shorter alkane from paraffin, but we've also got a very small alkene. And in fact, I'll just draw this C2H4 just so you can see what it looks like, because what we actually have in this is a double bond between the two central carbon atoms, which we don't have in paraffin or octane. So that's this one there. So you can see what we've done is broken down this long chain hydrocarbon into a shorter alkane molecule and an alkene. Now, this ethene that we've got, we can use that to make plastics. So this is a simple process of cracking, but for this to work, we need two things: plenty of heat and a catalyst. So we're going to just make a note of the things that we're going to use for this. So these are the requirements. So the first thing is heat. So we're going to have a very high temperature because we need to overcome those strong covalent bonds. And we're going to have that at about approximately 400 to 700 degrees C. So we're looking at 400 to 700 degrees Celsius for that. The second thing we're going to need is a catalyst. And the catalyst that we're going to use in this case is one called Aluminium Oxide. So that's Al2O3. I don't know if the 2's come out particularly well on the video. I'll shrink the screen just because then actually I can write a little bit more underneath. So the catalyst we're using is Al2O3. There. And aluminium oxide is going to act as our catalyst. Now these long chain molecules, they're going to split apart or crack on the surface of the bits of the catalyst. Now what we actually do is when we pass these hydrocarbons over the catalyst, we do it in powdered form. So that's just one thing to just make a note of here, that this catalyst is in a powdered form. And the actual hydrocarbons that enter are vaporized hydrocarbons. Now, a lot of the longer molecules produced from fractional distillation are cracked into smaller ones quite simply because there's more demand for products like petrol and kerosene, rather than ones like lubricating oil and diesel. So that's why we're actually going to do this process. But these are the two requirements predominantly we need. Very high temperatures and an aluminium oxide powdered catalyst, something that's going to speed up the reaction but without being used up itself. Now one thing that I've just said then that's really important is the word demand. Now often questions that you get asked in exams are about supply versus demand. So you may get given a table of information, it might tell you certain fractions and the approximate percentage that you find of those fractions in crude oil, and then the approximate percentage of the demand. And what you might have to do is look at how much relatively is in crude oil and then work out which one of those you're likely to crack. So you would find perhaps that you would use kerosene to supply extra petrol and oil and bitumen to supply extra diesel, because actually there's quite a high amount of those within the crude oil. Then again, oil and bitumen might be able to crack to form both petrol and diesel, because there is quite a significant amount of that in crude oil, predominantly so. So just be aware that a lot of the questions you get in exams are numerical. They'll give you percentages about the fractions and you might have to guess which one is cracked. But here in this video, we've just outlined the process. So you take a long chain hydrocarbon and via thermal decomposition, so using heat to break it down, we get smaller alkane molecules and alkenes as well, as we've had in this example. Okay, hope all that helps.